Section 3.6, Inverse Trigonometric Functions and Their Derivatives. Recall from Section 1.6 that the only functions that have inverse functions are one-to-one functions. Trigonometric functions, however, are not one-to-one, and so they don't have inverse functions. But we can make them one-to-one by restricting their domains, and we will see that the inverses of these restricted trigonometric functions play a major role in integral calculus. Now you can see here in figure 1 that the sine function, y is equal to the sine of x, is not one-to-one by using the horizontal line test. But if you look at figure 2, the function f of x, which is equal to the sine x, with the restriction where x is in between negative pi over 2 and pi over 2, is one-to-one. The inverse sine of this restricted sine function exists and is denoted by sine inverse, or we also call it arcsine. It is called the inverse sine function or the arcsine function. Now, since the definition of an inverse function says that f inverse of x is equal to y, implies that f of y is equal to x, then we have the following. We say that the sine inverse of x, which is equal to y, implies that the sine of y is equal to x, such that y is going to be in between negative pi over 2 and pi over 2, or the angle for sine is going to be in between negative pi over 2 and pi over 2. And now keep in mind that sine inverse x does not equal 1 over the sine of x. Now, if x is in between negative 1 and 1 inclusive, the sine inverse of x is the number that's between negative pi over 2 and pi over 2, whose sine is x. So, evaluating an inverse trig function is the same as asking what angle, i.e. y, did we plug into the sine function to get x. The restrictions on y given above are there to make sure that we get a consistent answer out of the inverse sine. We know that there are in fact an infinite number of angles that will work, and we want a consistent value when we work with inverse sine. Using the range of angles above gives all possible values of the sine function exactly once. If you're not sure of that, sketch out a unit circle and you'll see that the range of angles, the y's, will cover all possible values of sine, which you can see here in this unit circle. So let's take a look at this example here. So if we want to evaluate sine inverse of 1/2. So the first thing we're going to do is we're going to take a look at all the outputs where the y value is 1/2. So if we take a look at our circle, here we have negative 3 square root of negative square root of 3 over 2, and then 1/2, and that angle represents 5 pi over 6. And then over here we have square root of 3 over 2 and positive 1/2, and so therefore there's the other output that has a y of 1/2, and that angle is pi over 6. Now the other ones down below have a negative 1/2, and this is a positive 1/2. So we're only looking at the positive 1/2. Okay, so now the next thing that we need to do is we need to determine, okay, what is the angle, what's happening with this angle. So this angle that we can see here that it forms, you can see that it forms pi over 6. And then this angle forms 5 pi over 6 because that is this angle. Okay, so again, what we want to do is we want to be able to evaluate the sine inverse of 1/2. Well, basically what this is asking us is saying we are really asking what angle y solves the following equation. And we are restricted to the values of y above. We're restricted from negative pi over 2 to pi over 2. So here's positive pi over 2, and then here we have negative pi over 2. Okay, so what that means is if we're restricted from negative pi over 2 to pi over 2, that means we're only looking on the right side of the circle, which means we're not looking at this angle over here. We're looking at this angle. So since it falls within this range between negative pi over 2 and pi over 2, then therefore it's going to be pi over 6. So the answer here is pi over 6.